We talked about order of growth last week, but some students are apparently still not too clear. So let's take a look at an example today. So let me just quickly recap. To estimate the order of growth, we first identify the basic computation steps. Then we try a few small values, and then we extrapolate for really large n, and we look for worst case scenarios. Okay. Now, if you remember this code from count change, let me just quickly repeat. So the number of ways to count some amount of money with some amount of coins is equal to using number of ways to count using all but the first count of coins. So basically, you remove one from the count of coins, okay, added to using at least one coin of the first kind. So what happens here is that you take the amount of money you have, you minus away the first denomination, and you keep the number of kinds of coins the same over here. Right now, so this is pretty much how you would do it. Now, let's take a look at some small examples. Let's say we try count change 11.5. So 11 cents and 5 kinds of coins. So this becomes CC 11.4 and CC minus 39.5. Why? Because the first denomination is 50 cents. So this is minus 39, right? But this is 0 because you can't count negative coins. Then this becomes CC11 and this becomes CC minus 9 because second coin is 20 cents, right? So this is also 0. Then it becomes CC11, 2 and CC1, 3 because this now is a 10 cents. So this is 1, 3 and this is fine, right? Now this becomes something here. Let's wait for a while. And then this becomes CC1, 2, CC minus 9, 3. Okay, so this is 0 again. This is 1, 1 and this is minus 4, 0. This is of 0. This is 1, right? Now we take this one over here and try again. It's for CC11.1, CC62. Okay, this is 1, and this is 6.1. This is 1, 2, and this is 1, and this is 1, 1, and so forth. This is 0. Okay, so the answer is 4, right? And okay, this is a very quick example. What you do is that you actually do this again in tutorial. So hopefully this will be more clear. Now let's take a look at a really large n. Let's say CC 10,005. Okay, obviously you have something like this, right? Okay, it's a big tree. So now let's take a look at the steps. Okay, so first you work out the steps in the computation and you generalize. So you realize that this particular tree here will become something that looks like this. It's a full binary tree. A binary tree means that every node has 2 branches, right? One branch left, one branch right. Okay, and then subsequently at the bottom there you'll become smaller partial trees. So let's take a look at this structure. Now what's clear is that this tree is a bit lopsided. Now over here is longer and it's L. Over here is shorter and it's D. So what is L, what is D? Okay, it turns out that if you look at the pattern, right, the big D is actually A, which is the amount of money, divided by the largest denomination that you have. So 50 cents if that's 50 cents. And L is actually A plus the number of types of coins. Okay, why is this so? I think I will leave you to work this out by yourself. Okay, and you just follow the pattern and just go and you see what you would end up with. Alright. Okay, so now let's take a look. So for large amounts A, right, time complexity is equal to the number of leaves in the tree, which we know is approximately 2 to the L because let's take a look here. L is the largest side. So basically 2 to the L is the total number of leaves in this bigger tree, which has some gaps, right? So it's 2 to the L, full tree, minus some missing leaves. So it's this number, and this L is A plus N, and so it's roughly order 2 to the 8. Now, we are sure over here that these numbers are much, much smaller than this number, so this is okay. The key thing to realize is that in terms of space, there are 2 key sources of space. First is function calls. When you make a function call, you actually have pending operations, and these operations are kept in the stack. So every time you have a pending operation, you will take up 1 space in principle. So if it's n, if it's a problem of size n, you have n pending operations, or n minus 1 pending operations, then it's order n space, right? Now later on, you have data structures, and these data structures are actually kept in the heap. We'll discuss this later. For this part of the class, just count the pending operations, and then that will give you the amount of space you need, right? Okay, space complexity is equal to the depth of the entire tree, and which is L, which is A plus the number of coins. So the space is order A. Now, some Christians will ask, why is it the depth of the entire tree and not somehow the total number of leaves? It's because the way that the computation takes place is that it will go down, okay, to one side of the tree to the end, and it comes up and it goes down, it comes up again, it goes down, right? So it never really expands out the entire tree. It actually kind of computes each part, okay? Now, for homework or to think about this problem, what would you do, or what happens, right, if you only had finite number of coins? What would you do in order to solve the problem if you had only a finite number of coins, right? And how would this affect the order of growth in time and space?